few. So, welcome to my lecture. Today, this fourth class, that is the chemical enhanced oil recovery for the shale oil and tight reservoirs. So, already you have gone through some lectures and where you must have learned about the different properties, structure, and the potential for the shale oil and tight reservoirs. Now, why the oil and gas industries, they are looking forward for this extraction of oil from the shale oil and tight reservoirs? Because we know that the conventional oil reserve, that is the conventional reservoir from where we can get or extract the oil more easily, that reserve is gradually declining. So we have to go for some reserves which are not easily accessible. And these type of reserves or reserve basically sources is known as unconventional resources. So unconventional means we are unable to get it by conventional established technologies. And one of such unconventional resources are shale oil and shale gas and oil from tight reservoirs. And if we see that, particularly in the North America, like United States and Canada, they are having significant resource of this shale oil and tight oil reservoir. And particularly if we see the picture in the United States, it is observed that their shale oil has accounted over half of the country's output since 2010. So this particular figure or data that can tell you the potential of such type of reserve. Furthermore, it is the cost effective to extract. The most interestingly that in most of the cases, though it is a tight reservoir, the oils are very much light and there are some gas condensates that can be easily extracted. Easily means I want to say that is the cost effective way if you have the proper technology. Now this is the quite challenging, because if we see the typical picture here, there are some conventional and there are some, you can see that these are some conventional oil, conventional gas. Here also conventional non-associated gas, and here these are the tight sand oil or tight rich and the gas rich shale, oil rich shale, etc. So if we go for, just I am going to this figure, if we go for this particularly the permeability variation, so this can say that anyway this type of reservoirs are different from that of conventional natural gas and oil reservoir. So here this x-axis, that is the bottom line, shows that the permeability, and you can see that for the shale or tight gas sand, this permeability is very, very ultra low, maybe microdarcy or millidarcy or nanodarcy. So this particular information, this particular properties of the reservoir, this type of reservoir can tell you that obviously the technology, whatever we are conventionally using in natural, in conventional reservoir is different. Now the technology development that depends on the resource, as because of the very easy recovery, we are going for most of the conventional reservoirs, and there are significant, even after 30% recovery, the people are going for enhanced oil recovery with subsequent with the hydraulic fracturing. There are large number of different enhanced oil recovery or enhanced gas recovery methods are there, because this is under control, and significantly there are significant development in the technology, and we are trying our best to extract from this natural resources, these conventional resources. Now, on the other hand, if we go for the unconventional reservoir, so there, as the technology are different, and the cost of production that is significantly high, as you can go through, say, that is the, if you see that at present the crude oil price is around 65 to 70 dollars per barrel. So obviously you are expecting to continue the production, they must have the production cost below 40 or 50 dollars. But it is reported that the production from the shale oil reservoir or tight reservoir, the cost of production may be around $90 per barrel. So, depending, so this particularly the production planning, resource available, and the crude oil price, that all these parameters that basically controls that how we'll go for this unconventional reserve. But as we know, there is continuous decline, so at a time we have to go for such type of unconventional resources, and obviously for that the proper development of technology is very much required, that is different from the conventional technology. Now, if you see this picture, that is basically taken some previous data, EIA 2015. So they have predicted that with time, So there will be significant recovery from the tight oil reservoir. And if we compare the different other type of conventional oil, so there will some time will come where this production from this tight oil, that is the shale oil and tight reservoirs, will be higher than the conventional crude oil. So we have to be ready for this type of production, and for that development of the technology for the enhanced production should be there. Now, if we see the present data, particularly in the North America and in particular USA, so it is observed that there are some fields are there where extraction and exploration of hydrocarbon from this tight and shale formation are basically very, very promising, that are basically unlocking the vast oil and gas reserve that is which was previously considered as inaccessible. So this particular testing data or whatever maybe they have basically explored, that must show the way where you can get the significant amount of oil and gas condensate from this type of unexplored resources. Now, coming to the technology, I was going through the previous lectures. So there are different recovery methods are there, and out of which chemical flooding, that is a very important method which is conventionally used for the conventional reservoirs. And here the chemicals that are mostly used are surfactant, polymer, and alkali. And in combination of these different chemicals with the different blends, and right now there is another type of material that basically considered under this chemical flooding is the nanoparticle. There are different type of suitable nanoparticle. So what are the basic objectives of this chemical flooding? So basic objectives are, you have to increase the capillary number to mobilize the residual oil. Now this capillary number, you know, that is basically the ratio of the viscous force by interfacial force. Then the mobility ratio. For better displacement, for better sweep efficiency, the mobility ratio should be lower, and emulsification is another important mechanism that basically improves the displacement efficiency and obviously facilitate the production. Now, if we go through this slide, that is the total production. Total production depends on the so many efficiency terms, okay, multiplied by this original oil in place, that is SO VP by BO. And this efficiency terms are displacement efficiency, D, aerial sweep efficiency, vertical sweep efficiency. Now, this chemical method, different chemical methods, this aerial and vertical sweep efficiency, this can be improved by injection of different polymer solutions, and the displacement efficiency can be improved by use of surfactants or alkali, which basically improves the or basically reduce the interfacial tension, changes the wettability and emulsification. Now, this total efficiency obviously depends on all these three efficiency terms mentioned here. Now, these efficiency terms depends on so many parameters. So you can see that aerial sweep efficiency is a function of mobility ratio, different patterns of injection and production oil, directional permeability. Now, this particular parameter basically tells us that how this chemical enhanced oil recovery for the shale or tight gas will be different to that of the conventional chemical pure method that is applicable for conventional reservoirs. So this directional permeability, so I have already mentioned that this permeability is basically micro or nano level, millidarcy level. So this injectivity issue of the different chemicals is a major problem. Then pressure distribution and this cumulative injection. So this injectivity or injection is also is a very important parameter. So we have to take care of, considering the very ultra low permeability, we have to take care of the injectivity. We have to take care of the how this injected fluid cover all this area, that is to increase the sweep efficiency. And similarly, it is applicable to the vertical direction, where we are this aerial sweep efficiency is basically in the area, and vertical sweep efficiency is basically the this is the aerial particularly, and this is the aerial sweep efficiency, that is how much area is swept. For example, if you have some injection oil here, so you can see that this particular area is swept. So it is not satisfactory because these particular zones are not swept. So you cannot get the recovery from this particular unswept zone. And this is basically known as the aerial sweep efficiency, and this aerial sweep efficiency can be improved by injection of the different polymer solution by controlling the mobility ratio. And the same thing in the vertical direction, because of the different layers, different layers of different permeability. In the vertical direction, the sweeping is also basically important parameter, because ultimately how much total volume is swept That is most important to account for the total oil recovery. And then the volumetric sweep efficiency, which is a multiplication of the aerial sweep efficiency and vertical sweep efficiency, is the very important parameter. And even if all this area are swept, then also there is some limitation that basically, or there are some parameters that basically limits the recovery, and these are these particularly limits are basically controlled by the different parameters like primary depletion, the relative permeability, then viscosity of the different fluids, etc. And that is known as the displacement efficiency. And basically, we can, by chemical injection, particularly surfactant and polymer, if we basically change, improve the recovery. Now, this picture shows that this is particularly if the mobility ratio is not controlled properly, there will be early breakthrough, and there is viscous fingering is there, and you can see that the area is basically not swept properly. And this particular picture shows that how, so this is the basically microscopic sweep efficiency, or this is in the vertical direction, and this is in the aerial direction. And if this particular area, for example, is already swept, so here also, if you take this particular portion, particular figure shows the microscopic sweep efficiency, both in the macroscopic sweep efficiency, both in the vertical direction and horizontal direction. So here it is the vertical direction. This is the horizontal, this is the aerial direction, and this is the vertical direction. So we can get the macroscopic sweep efficiency or volumetric sweep efficiency. And say, for example, this particular area is already swept. Then you can see also there are, because of the rock fluid interaction, you cannot extract all the oil, and then you have to change the certain parameter, that is the reduce the interfacial tension, change the weightability, then to improve the mobility, there is some emulsification that basically improves the recovery. Now here you can, as you understand, that this mobility ratio plays a very important role. That is, the mobility ratio is written as the mobility of the injected fluid by the mobility of the displaced fluid. Now, very briefly, this polymer flooding, particularly the different polymers that are used, is polyacrylamide and polysaccharide. So this particular, here it is shown their typical structure. So the one feature that or characteristics of these polymers is that should be water soluble. Now, when a polymer will be water soluble, when there is a certain functional group that basically interacts with the water, forming hydrogen bonding. That basically then it will be water soluble. Here you can see that in the amide group, this basically form hydrogen bonding, and if it is a amide is basically hydrolyzed partially, then also it can form hydrogen bonding, and it is easily water soluble. Similarly, the polysaccharide, I am not going into the detail. There is the polysaccharide is a very complex structure. These are sometimes known as the biopolymers. So these biopolymers are basically also having some functional groups like hydroxyl, carboxylic acid, and they can form hydrogen bonding. And because of this hydrogen bonding, and because of their, you can see that the structure, they form a viscous solution. They form a viscous solution, and then because of the viscous solution, it can basically reduce the mobility ratio. Otherwise, there will be early breakthrough because of the very high mobility of the water compared to the oil. Now, this polysaccharide, polyacrylamide is basically, there are some properties. It is basically basically not biodegradable. Okay, that is the resistive to biodegradation, but they are susceptible to mechanical degradation, and the reverse is for polysaccharide. Now, if we go for the surfactant, so surfactant again a very commonly used, and there are the most importantly, you must know that what is surfactant. In a surfactant, there is a basically hydrophilic group, and there is a long chain hydrocarbon, that is the hydrophobic group. So this is basically oriented at the oil-water interface with hydrophobic part. Hydrophobic part is oriented towards the oil, and this hydrophilic part is oriented towards the water, and it basically reduces the interfacial tension, and it also sometimes forms also these micelles also when the concentration exceeds the critical micelle concentration. Now, the surfactant in the different modes it can be used, and it can be if the concentration is above the critical micelle concentration, then it is known as the micellar flooding. And you know that surfactant, it can also having some foaming properties that also significantly improve the mobility ratio, also by improving the viscosity of the chemical slug. So then you can get the both the benefit, that is the reduction of interfacial tension, weightability alteration, emulsification, at the same time the viscosity improvement. And out of these different chemicals, they can be combined, as I mentioned, they can be combined altogether in a different mode. For example, this A is, that is the alkali surfactant, then SP, that is the polymer surfactant polymer, then AP, that is the alkali polymer, and the most commonly used as the ASP, that is the alkali surfactant and polymer, where all these mechanisms of the chemical UR, that is the mobility improvement, IFT reduction, weight alteration, emulsifications are covered. So here, this mechanisms of surfactant flooding is shown here. You can see, as I mentioned, this the IFT reduction is a very important mechanism. Then rock weightability alteration, and then emulsification of the oilic phase, that basically improves the mobility. So here, this picture can show that when your interfacial tension is very high, then what happened? Because of the high interfacial tension, generally these oil droplets becomes rigid. Then by application of the viscous force, that is usually by water injection. This force in this direction is not sufficient, because you can see that this pore throat diameter is less than the diameter of this oil droplet, and the viscous force is not sufficient to force the water, this oil droplets or oil bulbs to basically flow through the this pore throats. And in this case, if we use some surfactant, then what happens? These surfactants are absorbed at the oil-water interface. The surfactants are adsorbed at the oil-water interface, as their orientation is basically, again, this hydrophobic part is towards the oil and hydrophilic part is towards the water. Then what happened? They basically reduces the interfacial energy. They reduce the and under this condition, they will be basically quite flexible. And because of this improved flexibility, now application of the this viscous force, they are deformed. You can see they are deformed, and by application of viscous force, they can now easily move through this fine force. So in this way, they basically improves the displacement efficiency. Then weightability alteration, they basically change the weightability of the rock, basically oil weight rock to the water weight, because you know that if the rock is oil weight, then obviously the recovery is less, and if it is water weight, then the recovery is higher. So and it is particularly observed that the shale oils, basically, if you see, it is observed that the shale formations are typically oil weight or mixed weight. Now, because of that, this particular mechanism, that is the weightability alteration, basically plays a very important role. And here, there's some picture basically shown at the bottom will basically give some idea or realistic picture. Or here you can say this is the shale, and this is the oil extracted from this shale reservoir. And there are some other images of the shale oil rock. So here you can see, at least if we do not enter into the microscopic level, from the naked eye, you can see that this oil are basically attached on the rock surface. Okay, and this is because, again, related to the some zeta potential values, their interaction of this oil with the reservoir rock, etc. Because you know that most of this shale, okay, there are significant amount of the, other than whether it is the carbonate or sandstone, there are significant amount, the clay component is there. And this clay component is basically, they interact with the some asphaltenic or resinic components of the crude oil, and they are tightly adsorbed or basically attracted, and this occurs for a millions over the time, and subsequently they are basically converted to the oil weight. And this surfactant injection, they basically significantly improve the recovery, particularly the improve the displacement efficiency by lowering the IFT, then altering the weightability. That is the most important parameter here, that is altering the weightability and this emulsification. Now, these are basically some data is taken from some recent paper. This paper. So here you can see that particularly there are two different type of the shale rock. One is the carbonate, and another is the siliceous shale. Okay, and you can see that there are different types of rocks are there, particularly this data, if you refer other figures, earlier figures. So this is taken from some fields of USA. So in the most cases, so you can see that these are basically is of intermediate weight. Okay, now by different surfactants. Okay, now the selection of the surfactant is very much important. For that you have to perform the different study so that they basically get attached on the rock surface and displace the oil from the rock surface, and accordingly that is measured by the how to changing the contact angle. Now here you can see that for some typical values, say for example, I think they have taken this is as a base case here, where base case here somewhere where the water in presence of water, the contact angle is around 121, and then by use of the surfactant, say anionic surfactant with some typical surfactant, it is reduced to 55. Then some anionic and non-anionic surfactant, it is reduced to 47. Then by another anionic surfactant, it is reduced to 50, and by some cationic surfactant, it is reduced to 39. And this is some another cases. There are two different cases are taken here. You can see this is the WC means Wolfcamp rock. And this is the EF. EF is the Eagle Ford particularly formation. And here also there is significant. So here you can see that that is the selection of the surfactant is very important, and selection there particularly interesting. So significant lab study is required to get the proper understanding or to proper screening of the surfactant so that we can get the maximum benefit. Now here this picture shows that particularly this emulsification mechanisms. So emulsification mechanisms, because of the emulsification here also again the mobility of the trapped oils are increases, and that basically significantly improves the recovery. Now the question is, that is the main part, particularly that so far we have discussed the just important mechanisms of the different chemicals methods. Now as I mentioned earlier, this particular this is a unconventional, this shale and tight reservoirs are unconventional, so significant challenges are there. Okay, so what are the, let us see that what are the challenges of the chemical recovery from these shale and tight reservoirs. So first parameter, that is, if we touch the first parameter, is that ultra low permeability. As I mentioned, that this shale and tight formation often have the permeability in the range of nanodarcy and microdarcy. And not only that, along with this permeability, if you see that porosity, the porosity is also very less because of the very fine grains, and it is packed, okay, by high pressure. And not only that, there are significant amount of the clay materials are there. And because of this porosity, because of the low porosity, that is the holding capacity per unit volume of the pore. Okay, that is very much less compared to the conventional reservoir. So that are the basically quite challenging. That is, you have to. There are huge, maybe there are significant volumes are available for this extraction, but the amount of oil per unit volume of the reservoir may be different. And the most important is the lowest permeability, very ultra low permeability, that is the nanodarcy or microdarcy. Now, here, what can be done? We can use the different chemical agents such as surfactant, polymers, and alkalis that basically, if we use, so we have to be very careful because we have to take about the penetration of this chemical so that now, because of this low permeability, you know that if you go through the definition of the permeability, so ultra low means it will not allow the injected chemical sludge, either it may be surfactants or polymer, to enter into the formation easily. So accordingly, you have to. So accordingly, you have to design some surfactants and polymers where the injectivity is not a problem. So that is, I just want to mention that if we, I had gone through the typical structure of the some polymers, typical structure of some polymers. So there are some long chain polymers are there. Now here you have to have some control over the polymer. That is, you have to check the effective hydrodynamic diameter of the polymer. You have to design, you have to synthesize, or you have to tailor-made, you must have some tailor-made surfactants or polymers where hydrodynamic diameter should not be very high. Then only it will be able to flow through these fine pores. And it has been found that under this constraint, this use of the some nanofluids and microemulsions that are having very with low viscosity formulation to enhance the injectivity and the penetration into nanopore media. That is our objective for this. That is the point you are planning for the recovery from the shale or tight reservoirs by chemical methods. So the injectivity or the flow of the chemicals through the this fine pores and with relatively ultra low permeability is quite challenging, and according to have to design. So significant lab study is required. Then incorporation of the smart fluids capable of navigating the complex pore structure and fracture network. So that is basically smart. What do you mean by smart fluids? Smart fluids is nothing but where you are controlling the different parameters, starting from the different chemical composition to the salinity, their effect of salinity, that basically you must aware of the low salinity water flooding. So and particularly you must have heard about the smart water flooding, where basically the multivalent and divalent ions plays a very important role. So here also that type of ionic composition, then composition of the chemical should be perfectly considered based on some laboratory study with proper designing, so that it can be effectful and then to overcome this ultra low permeability. Next is that the problem with the high capillary pressure, because of the very fine, as in the morning session going through the lecture, that is this the capillary pressure. Okay, because you know that when you are having this fine force of the tight reservoir, so obviously the capillary pressure will be high, and because of the tight pores, it exhibit the extremely high pressure, and then basically this traps the oil tightly within the rock matrix, and then making it difficult for the chemicals to mobilize or displace the trapped oil. So high capillary pressure means you have to have significantly you have to think to reduce the capillary pressure. So how this capillary pressure can be reduced? So that can be reduced and because high the capillary pressure means these oils are trapped, and by conventional method you are unable to recover this trapped oil. Then in that case, the design of ultra low interfacial tension basically surfactants or co-surfactants or surfactant polymer combination that basically lower the capillary forces and mobilize the trapped oil. So this type of study is very much required, and proper formulation or proper design is very much important. Then application, particularly you have to select the perfect surfactant with high capillary number efficiency under the cell reservoir condition. Next, another very important when we are talking about the different chemicals, and if you again go through the conventional reservoir where you are having either sandstone, carbonate rock. So particularly for when there is a sandstone rock, basically we prefer to use anionic surfactant or non-anionic surfactant, and for carbonate reservoir some cationic surfactant because of the oppositely charged ions that basically leads to adsorption. And this adsorption of the chemicals that basically causes the significant problem because these are lost, these chemicals are lost by this adsorption. They do not play in actual to their actual mechanism for the say either reduction of interfacial tension or this mobility control, as they are adsorbed on the rock surface. Okay, and if we compare here with the cell, one side there is a cell reservoir rock and the conventional. Here, the surface area and in the cell or tight reservoir, the surface area and the mineral content are particularly surface area is very high because of the fine grains. The surface area, and you know that every chemicals they are basically adsorbed on the rock surface. So that basically lead to significant adsorption of the surfactants and polymers on the rock surface. So basically reduce the available concentration. This basically if it is lost by adsorption, so it is basically effectively this mechanism would not play significantly, and then you have to inject additional surfactants or polymers, and that basically leads to the increasing cost and the reducing efficiency. So here, particularly to concern that, particularly when you are planning for this recovery, this chemical different method for shale reservoir rock, so you have to use some additives that basically or typical polymers that are having the very low adsorption, or you have to some additives that basically surfactant agents that basically reduce the adsorption of the polymers or surfactants. And particularly here, these clay materials are significantly there. So this interaction, how they are interacting with the clay materials, that proper understanding should be very much required. And one thing that particularly done, you can go for the pre-flush or co-injection of strategic saturated adsorption sites. Okay, this optimize the chemicals. So what you can do, you can go for some pre-flush. Pre-flush means particularly you can say some low cost chemicals that have having some absorption capacity on that particular rock. You flush with that so that their active sites may get saturated, or adsorption site are saturated, and then you can use the optimal use of this different chemicals. Now the degradation and stability. So shale often have very high temperature, variable salinity, and then reactive minerals. So the chemicals may degrade thermally and chemically and reduce their functionality. So accordingly, you have to develop some thermally and chemically stable surfactant and polymers that basically shows the resistance to the high temperature and salinity conditions. So here, the use of different deuteronic surfactant or non-ionic surfactant, and specially formulated, that I mean, so you have to go for some tailor-made surfactants or polymers that basically shows the performance at the under the harsh condition of the reservoir, that is the high temperature and high saline condition. Now, water rock interaction. So many shales contains the that is the clay. So clay basically soils in presence of water, and which react with the injected fluid, that is water, and then there is a hydration of the clay, and there is swelling of clay, and they have some detrimental effect on recovery because of the pore blockage and permeability reduction and clay soiling. So ultimately hinders the flow. And so here, how this problem can be tackled. So you have to inject some clay stabilizing agent, some chelating agent, some pre-treatment fluids to prevent the swelling and migration of the clay materials. So that is very much important. Otherwise, already we have mentioned that it is the permeability or porosity is very less, and what that if there is a significant soiling of the clay by injection water, so that basically reduces the efficiency of the recovery significantly. So here different anti-soiling agent that is to be used so that you can get some enhanced flow. Now the shales are typically oil wet. Okay, that is another challenge, or mixed wet with organic matter, that is the kerosene present, as you have learned. So chemical interaction of the wettability is difficult and may require the specially designed surfactant or nanoparticle formulation. So you have to go for some advanced study to find out the suitable surfactant or nanoparticle basically for this typical reservoir. It may happen if you go from one type of reservoir to other reservoir, their properties are totally different, and then you have to have different design of the surfactants nanoparticles. So you have to have the tailor-made surfactant and nanoparticles that are capable of altering the wettability from the oil wet or water wet. So different smart chemicals system that responds to the reservoir condition to achieve the desired wettability shift. So this type of study is very much required. Then the fracture network. So oil is stored in the matrix but flows through the natural and induced fracture. So chemical, you are basically must navigate the complex fracture network to access the matrix, and particularly when there is a natural fracture or induced fracture. Now for chemical flooding, it may happen that without entering into the matrix, they may bypass. Okay, so you have to accordingly you have to use the proper smart chemicals like this nanofluids or microemulsions, so that it can if there is a high pores are there, they should reduce the permeability of that zone. So the mitigation is design of chemical systems for the fracture dominated flow, including setting and soaking strategy to allow imbibition into the material. Sometimes we can go for some this profile modification also. And sometimes the viscoelastic surfactants, foams, and nanofluid-based systems can enhance the sweep and matrix penetration. Now, the economic constraint, the high cost of the chemical formulation and uncertain incremental recovery. Okay, uncertain incremental, here the incremental recovery by this chemical method, as it is tested by different study or laboratory, it is found that it is much less compared to the conventional reservoirs. So one thing is the high cost of the chemicals, other is the uncertainty. So these are the basically some limits. So these limits basically controls the commercial viability of the process unless the recovery is substantially high. Okay, and so here you can, accordingly the proper study, you have to go for some hybrid UR method like chemical and gas injection to reduce the chemical loading while maximizing the effectiveness, and then apply the techno-economical modeling and sensitivity analysis for optimizing the chemical type, concentration, and sludge size. So proper designing their economical study, their feasibility study is considering the cost of the chemicals, cost of the portion, cost of the oil price. You have to think that whether it is feasible or not. Then the fluid compatibility. So for fluid compatibility, so that is already I mentioned, that is whatever chemicals you are injecting, that should not react with the differently, and there should not be basically uncontrolled absorption, etc., that is lost. So you have to for that the proper flushing is very much important, so that it basically basically after pre-flush the condition will be much in favor of some chemical injection, and then ultimately it can improve the recovery. So it is observed that the field trials, there are only limited field trials. Basically, we actually learn from the different successful projects, that is with the help of particularly the machine learning and data science. If there are successful projects are there, so that basically says that what are the limitations, what are the lacuna, what are the positive things are there for different types of but if you don't have such type of data, then getting of some idea, or basically I can say that it is a very, very risky to go for some chemical methods. So then to avoid this, we have to go for some advanced reservoir simulation, some core flooding experiment, some pilot study, and then that basically helps that whether it will be quite profitable for this particular study. And there is basically some, there is data sharing by different research groups, some collaboration, then integration of the lab, both academic and industry, the institute interaction, that basically significantly help to proper design or proper planning. Now, this already discussed, and here particularly the screening, that is how the different surfactant typical it can be screened for particular application. Here some typical recovery that is performed in the lab study that is taken from some paper here. Here you can see that additional this recovery is 13% is quite high for this particular case. But on the other hand, if you compare to the conventional reservoir, it is much less. Okay. But for this unconventional reserve, this 13% is quite high. And sometimes there are some chemical blends are reported in some study. And in some cases, some microemulsion and nanofluid, as I mentioned, they particularly helpful to alter the weightability and mobility control. There sometimes some repeated studies are there. And this is a typical comparison of some unconventional and conventional reservoirs. And so here, this particular pictures shows that particular design. So you have to go for this rock characterization, you have to go for the crude oil characterization, you have to go for the shale core collection, you have to go for this surfactant particular nanoparticle this composition. So every study you have to perform, and ultimately you have to go for either spontaneous emission or forced emission, and you have to check that what is the oil recovery. So significant study is lab study is very much required before considering a plan. Now, the main limitation, as I mentioned here, that is the penetration magnitude, and because of the low permeability and porosity, the penetration is very low, so that is quite challenging here. And then the mode of fluid injection, I think in the morning section, there are some classes on half and puff method that is particularly applicable for carbon dioxide gas injection. But for chemical method, it is basically for flooding is basically more appropriate. But the problem is basically penetration depth and their injected soon. So that is, so this particular parameter are basically we have to consider for successful implementation of the chemical oil recovery from the shale and tight reservoir. And because this area particularly is it's so far unexplored because of the high production cost, because production cost when you are already this cost of production from shale or tight is high because of the very ultra-low permeability. On the other side, if you have the chemical, consider the cost of the chemicals, so that basically significantly improve the cost. So that way, you have to be ready with the technology, but you have to at the same time to make it profitable, you have to wait for what is the crude oil price, and you have to much cut. You have to reduce the production cost by developing the established technology, and particularly when the crude oil price on the higher side, under that condition only this chemical EOR method from the shale and tight gas may be tight reservoir may be successful. Okay, thank you. And if you have any questions, so because we are running late, so already 1 p.m. So you have any question, you can contact me through email or phone. Sir, all the questions. So thank you. So this is the end of the day, and tomorrow again we'll be joining at 9 o'clock. That's 9. Thank you all.